acceleration as a function of position. So say we're given a of s instead of a of t, and that equals 100 e to the negative 0.3, not t, s. 100 e to the negative 0.3 s. And initial velocity equals 0. Then we need to find velocity. Yes, we'll say velocity as a function of position. So this time we're doing an integration not over time, but over position, because that's what these two were given to us. So we won't be able to just straight up integrate the acceleration equation and get velocity, because that's what we would do if we were integrating over time, like over here. In this case, we have a different relationship to use. So instead of a equals dv dt and integrating that, we're going to have a equals v times dv ds, and we integrate that. So we see there's that extra v in there. So in that case, it won't be just a direct integral of a dv. We'll have an integral of v times dv, so that'll end up with a v squared. So let's write this out. We're going to use a equals v dv ds. And so we need to separate and integrate. So that means by separating, we want to get everything with s on one side and everything with v on the other side. So we'll say v dv equals, and then this ds comes around and gets multiplied by the a, but a equals 100 e to the minus 0.3 s. So we have 100 e to the minus 0.3 s ds. So we just plug that 100 e to the minus 0.3 s in here for a. And now we have to integrate each side. All right. So doing this now, if we integrate v, we actually get v squared over 2. So v squared over 2 equals, and now we do this integral with respect to ds. Well, we know that the integral of e to the x is e to the x. But now here there's this 0.3 in there. And so we have to use chain rule. So integrating this, we'll get 100. And then we have to divide by that negative 0.3. E to the negative 0.3 s. And then plus constant. Okay, so this is because the way we got that 100 over the negative 0.3, if you think about taking the derivative of this one, then we would be using chain rule, and the 0.3, the negative 0.3 would go and multiply in front, and then it would cancel with the 1 in the denominator, and then you'd be left with the 100. So that the derivative method gets us back to what this would be. So if you're not familiar with chain rule, go ahead and review that. But now we need to solve for this plus constant. And we were given that initial velocity is 0. So we can go ahead and plug that in and say to solve for the plus constant, we know that if v of 0 is 0, then on the left side of the equation, we would just get 0 equals, and then e to the 0 power is 1. So we'll just have 100 over negative 0.3 plus constant. So this gives us that the constant equals 100 over 0.3, the positive version. It does not matter if the negative sign is in the denominator or the numerator. Typically, you would put it in the numerator. So one thing that we can really, if we do here is, this is 333.3, like that. So then resolving, we will plug all of this back in here, and we have v squared over 2 equals negative 333.3 e to the negative 0.3 s, and then plus the constant plus 333.3. So simplifying that, we can pull out the 333.3 and multiply. That's going to be by times 1 for here, and then minus e to the negative 0.3 s. So we just combine those terms to simplify. But now we still have v squared over 2. We don't have actually just v. So we need to now solve for v. So we have to move this 2 to the other side and then take the square root. So we'll get v equals 666.7 times 1 minus e to the negative 0.3 s. And that will be square rooted. So this equals velocity as a function of position. So you can see it's different than if we just straight up integrated with respect to t, because the form when you're integrating using a different relationship, the integral is going to look different.